Now let's look at example 2, and this is page 84. So you're going to take those imaginary numbers and you're going to have to do all 4 operations with them. So you'll have to add them, subtract them, multiply them, and divide them. So that's what we'll do in the next few examples. Now there is something called a complex number. And a complex number is when you mix a real number with an imaginary number. And they're written in the form A plus BI, where the A is the real part and the BI is the imaginary part. Now, whenever you're adding or subtracting complex numbers, the thing you have to keep in mind is you're going to add or subtract, pretty much combine, like terms. So when I look at this problem, I see 6i. The thing that would be a like term, the term that would be a like term with 6i would be this 9i right here. And I need to watch out for the symbol in between because that's how you combine the like term. So I'm going to add 6i plus negative 9i to get negative 3i. And then I will look at negative 4 plus negative 2. And negative 4 plus negative 2 is negative 6. But usually your answers will ask you to write it in this form, A plus BI. So that means put the real part first. So I would just write this as negative 6 minus 3i. In example B, you're being asked to subtract. So the one thing to remember, and one thing I like to do, this negative distributes to both parts of that second term. So it might be helpful to rewrite this problem as 3 minus 2i plus 4 and then negative times positive minus I. Then look to combine like terms. So negative 2i minus I will combine to be negative 3i. And then I will combine 3 and positive 4 to be 7. So my answer is 7 minus 3i. How is adding and subtracting complex numbers similar to adding and subtracting binomials? We're going to add like terms. It's very similar. You're going to treat the I like an X. So treat the I like an X. So turn the page. Now let's look at multiplying. So whenever you multiply complex numbers, we'll multiply it the same way that you multiplied binomials. So it looks like on example 3, part A, I need to distribute. So I'll distribute 2i, 2/5 I times 10, and 2/5 I times negative 5/2. Well, 2/5 times 10 is 4. So I'll have 4i, and 2/5 I times negative 5/2 is a positive 1. And then, oh wait, it's negative 1. Just kidding. Rewind, delete. Okay, 2/5 times negative 5/2 is negative 1. And then I times I is I squared. Now, if we were just multiplying binomials, then we would be done. Like if I truly was an X, then I would be done. However, we have defined I to be the square root of negative 1. So then if I is the square root of negative 1, then I can expand that idea and come up with a value for I squared. I squared is the square root of negative 1 squared. And when you square a square root, it cancels out the exponent and the square root. And so we're just left with negative 1. So you're going to multiply the same way that you always do, except anytime you see an I squared, we're going to replace it or substitute it with negative 1 for all I squareds, because I squared equals negative 1. So you might even want to get a nice special pen. I squared equals negative 1. Draw some clouds around it, highlight it, do whatever you can. So that means in my problem here, I'm not finished. I've got some work to do. So I've got 4i minus 1 times I squared is negative 1. So this simplifies to 4i plus 1. For part B, I have two binomials being multiplied together. So again, I'm going to distribute. 1/2 times 1/2 is 1/4. And then 1/2 times negative 2, I is minus I. Then I have positive 2i times 1/2 to be plus 1i. And then I need one more color. 2i times negative 2i is minus 4i squared. So then I can look through and I combine like terms. I have a negative I and a positive I. Those they cancel each other out. So I'll have 1/4 minus 4i squared because these cancel each other out. Now I'm going to replace the I squared with a negative 1. So 1/4 minus 4 times negative 1. Simplify that a little bit more. 1/4 plus 4, because 4 times negative 1 is positive 4. And 1/4 plus 4 is equal to 4 and 1/4. Okay, now let's talk about simplifying the quotients. So we're going to need to draw some divider lines here. To simplify a quotient, you might be looking at this and think, oh, well, that looks pretty simple with me. The thing is, though, is that having an I in the denominator is improper notation for this level of math. So we need to figure out a way to get the I out of the denominator. And we do that through a process called rationalizing the denominator, which is simplifying the quotient. And so to do that, you're going to multiply the numerator and the denominator by the complex conjugate. Let me tell you what a complex conjugate is. Complex conjugate, that's a new word. Okay, so complex conjugate looks like this. So if I have my regular complex number a plus bi, its complex conjugate is a minus bi. So the real parts are the same, the imaginary parts are the same. The only thing that's different is the plus. One has a plus and one has a minus. So that's what we'll do to simplify the quotient. And this process, again, is called rationalizing the denominator. So if I look at my denominator on part A, the denominator is 2 minus 6i. So the complex conjugate for 2 minus 6i would be 2 plus 6i. So I'll multiply the numerator and the denominator by 2 plus 6i. So I'll distribute in the numerator, and then I'll distribute in the denominator. 80 times 2 is 160, plus 80 times 6 is 480. I over, then I need to distribute down here. 2 times 2 is 4. 2 times 6i is plus 12i. Negative 6i times 2 is minus 12i. And negative 6i times positive 6 is negative 36i squared. So then I'll simplify what I have. 160 over 480. Erase. Try that again. 160 plus 480i. In the denominator, I have a positive 12i and a negative 12i. Those two terms will cancel. So 4, and then minus 36i squared, I can replace the I squared with a negative 1. So negative 36 times negative 1 is really positive 36. So plus 36. So now I have 160 plus 480i over 40. So then I'll think, okay, can I simplify this any further? Well, I can. I can divide 160 by 40. 480 is also divisible by 40. So if you can divide both parts by what's in the denominator, go ahead and simplify. 160 divided by 40 is 4. 480 divided by 40 is 12. So we've got 4 plus 12i for part A. Part A, party, haha. Let me zoom out. Now we'll do part B in this space over here because I kind of ran out of space. So on part B, I need to be multiplying by the complex conjugate. So the complex conjugate of negative 1 plus 2i will be negative 1 minus 2i. So you only change the symbol in the middle. You won't change the symbol on the front. So the only thing that changes is the plus to a minus. So I'm going to do my work over here. So 4 times negative 1 is negative 4. 4 times negative 2i is minus 8i. 4 times, negative 3i times negative 1 is plus 3i. And then negative 3i times negative 2 is plus 6i squared. That's the numerator. Denominator, multiply everything out. Negative 1 times negative 1 is positive 1. Then I'll have plus 2i. 2i times negative 1 minus 2i. 2i times negative 2i is minus 4i squared. If I simplify the numerator, I've got negative 4. Negative 8i plus 3i is minus 5i. And 6i squared is the same as 6 times negative 1, so minus 6. Denominator, 1. The 2i's cancel. And then negative 4 times negative 1 is positive 4. Simplify everything a little further. Negative 4 my pen died for a second. Negative 4 minus 6 is negative 10. Minus 5i over 5. Divide everything by 5. I get negative 2 minus I. So that is for B. So why do you multiply the numerator and denominator of a complex fraction by the conjugate of the denominator? Because it gives you two terms, or two middle terms, like the 12i and the negative 12i, that will cancel each other out. Two terms with i's that will cancel. So if you noticed in that first one, we had a 12i and a negative 12i. Those i's added out, and the I squared turned into negative 1. Happened again over here with the, I need my highlighter, with the 2i and the negative 2i. Then I had an I squared that turned into a negative 1. And so now all my denominators are real numbers. Finally, there's something called the sum of squares. Now, you guys learned about the difference of squares a couple lessons ago, but did you know that there's something called a sum of squares? I bet you didn't. So the sum of squares is another way to factor something with two terms, but it only applies when you have a sum, which means plus, and squares, which means perfect squares. So it'll follow the form a squared plus b squared, and it will factor into a plus bi times a minus bi, where a is the square root of a squared and b is the square root of b squared. So let's factor. Take the square root of both sides, or of both parts. The square root of 4x squared is 2x, so I'll have a 2x and a 2x. Square root of 25 is 5, but it's a sum, so these need to be 5 i's. So make one a plus, make one a minus. So 2x plus 5i, 2x minus 5i. Then on part B, I don't see perfect squares, but I do notice that there's a common factor in both of those. So I could factor out of 2 from the whole thing to be 2 times 4y squared plus 9. And now 4y squared is a perfect squared, 9 is the perfect square. So I can factor that into 2y plus 3i and 2y minus 3i, and then just bring the 2 down. Now, why does it do this? Okay, well, let's take that 2x plus 5i and 2x minus 5i. Let's see what happens if I multiply that out. So let's check our work. 2x plus 5i, 2x minus 5i. What happens when I multiply that out? 2x times 2x is 4x squared. 2x times 5i is minus 10ix. 5i times 2x is plus 10ix, and 5i times negative 5i is minus 25i squared. And then if you notice, whenever we multiply this out, I get two terms that cancel each other out again. So we get 4x squared, and then I squared is negative 1, so this is 4x squared plus 25. So that's why it factors into the i's, because it would give those two middle terms that will cancel each other out. Now, example 6 has you put that skill to work in solving a quadratic equation that's going to have some complex solutions. If it is a sum of squares, we can solve it by sum of squares. So I can solve this by factoring. So let's factor. The square, x squared plus 49 is a sum of squares, so x and x, plus 7i minus 7i equals 0. To solve, either this first parentheses equals 0, the second parentheses equals 0, or both. So when we solve, we always act like both equal 0. So we'll say x plus 7i equals 0. Subtract the 7i on both sides, we get x equals negative 7i. For the second one, x minus 7i equals 0. X equals positive 7i. Done. For 9x squared plus 25, it's another sum of squares, so I'm going to factor it. 3x and 3x, 5i, 5i, 1 plus, 1 minus, and solve. So set each one equal to 0. 3x plus 5i equals 0. Subtract 5i on both sides. 3x equals negative 5i. Divide both sides by 3. X is going to be negative 5i over 3, or negative 5/3 I. Both are the same. For the second part, 3x minus 5i equals 0. Add 5i on both sides. 3x equals 5i. X is going to be 5i over 3, or 5/3 times I. Both are the same. That's one way to solve those. The other way, if you don't want to factor, you could isolate the x. So let me do that second one again without factoring. So if I had 9x squared plus 25 equals 0, as long as you only have an x squared and not an x, then you can still solve by just isolating the x squared. So I could go ahead and subtract the 25. 9x squared equals negative 25. Divide both sides by 9. X squared equals negative 25 over 9. Then I could take the square root of both sides and get x equals plus or minus the negative I can handle by taking an I out front, and then I have the square root of 25 over 9. To take the square root of a fraction, you take the square root of the top and the square root of the bottom separately. So the square root of 25 is 5, the square root of 9 is 3. So plus or minus I square root of, plus or minus I 5/3 or plus or minus 5/3 I. Either one of those ways are appropriate. Good luck with the section. If you need anything, schedule a help session, reach out for help. And also a reminder, you can click on the link on the homepage and see if anybody has asked a question about a specific homework problem. Have a great day, and I'll see you guys soon.